All right, let's get started. Um, Hope you all had a nice weekend. And this week of talks will start with Kirby Banman, who's a master's student here at RLAI, and he's going to tell us about covariate shift non-stationarity.
This is true. All right. So, hello, folks. Some of you already know me, but just in case, I'm Kirby Banman. I'm supervised by Martha White. And today we're going to talk about a very simple supervised learning problem with an equally simple non-stationary component. And we're going to try to turn a tiny bit of a dynamical systems lens on it. I'll be switching between whiteboard and slides for the presentation. Hopefully that's a bearable experience. And just as a request, if you've seen like problems or analyses like what I'll show, I'd really appreciate if you shared them during the Q&A or later. So yeah, first our learning problem. I'm just going to hit stop presenting here so you can see me, hopefully, I am the thing on screen now. Yeah, so.
Just to interject, if Google has made a decision for you in which it's showing this in like a tiled version, please select speaker view or something so that you can view Kirby's whiteboard in all of your screen.
Yeah, that's a good point. Okay, so hopefully now you're full screen mode and you can actually read what's on the board here. First, just our learning problem. So we are in the land of linear regression. So our target function, this blue line on these axes, has, well, it's a line. We're in linear regression. And our model is also a line. And we're sampling from a domain distribution that's uniform down here. So let's start writing this. Yeah, we're sampling on the domain, just uniform from negative A to A. I'll just write that as x sub t, t being a training iteration, is uniform from negative A to A. And for a given sample, our training target takes values y sub t. I'm just going to write here theta star 1 xt plus theta star 2. So it's a linear model. Our optimal weights are theta 1 star and theta 2. This is all scalars. Everything is scalars. There's no vectors here. Plus a tiny bit of observation noise nu. Probably you won't be able to see it on the screen over there, but that's often shown as a little Gaussian distribution. And our model values take predictions y hat sub t, parameterized by our model weights, theta 1 and theta 2. So that is at least the stationary form of the problem we're going to be working with. And it isn't a problem if we don't have something to do. So what we want is the argmin theta in R2, which minimizes the squared difference between our target values and our predictions. Again, it's all scalars, so this is just a normal squared difference. There's no norms. Oh, this is missing an important component. Argmin theta in R2 sum. Yeah, we want to minimize the total observations here. So if we find the minimum over a large enough sum, we'll converge. And if this, in a stationary version of this, we can solve it in closed form by just taking a large enough sample and solving that closed matrix form that we all know and love. But instead, we're going to do something a little different. We're going to say that we know that there exist hyperparameters, eta and mu, for SGD with momentum. So this being learning rate, much better mu being our momentum. There exist eta and mu such that this will converge. Which converge. And something that, well, I guess to be clear, what we mean by converge is loss goes down. Everything is happy. So something that we can wonder on top of this is what about non-stationary x sub t? A little bigger. What about non-stationary x sub t? Question mark. So that's going to be the focus of this talk. We're going to focus on a very particular kind of non-stationarity. And as a note, theta star is fixed. The target it doesn't change, just the non-stationary, the domain distribution will be non-stationary. So I'll write that. Theta star is fixed. Okay, feel free to ask any questions about the setup so far. I think this is like ML 101 day one kind of content so far, so it should be very familiar. And if it's not, that's a sign I need to clarify something. So yeah, feel free to ask any questions.
So Chaba asked, before you got to the non-stationarity part, that in the want part, does the sum go to infinity or some finite number?
Oh, excuse me. That's in the chat?
Yeah.
Yeah.
I mean, I can ask a question if you want. So just looking at that sum, it seems that there is some noise. So no matter how you choose the parameters, that sum is going to be infinite, I think. So you probably want to take the average and let the t, capital T, go to infinity or something like that, because otherwise this doesn't work. And then limes stuck in the limes, n goes to infinity before that, because you want to emphasize that n is infinite or something. But if you just sum up to everything, then it doesn't work.
That is totally true. My bad.
That's all right.
Okay, so we have linear regression, and we have a goal that converges, thankfully. Now, we're just going to make a small modification to the problem by introducing non-stationarity. We were going to talk about two non-stationary forms, one for the sake of its intuitive interpretation and another for its maybe surprising results. And I've realized 20 minutes is very short, so we're going to go straight to the second one. So recalling that theta star will be fixed and the non-stationarity is in x sub t, I'm going to draw another vertical axis. I apologize. I don't have a 3D whiteboard. You'll have to imagine this as protruding out or something. But this is training time t, and our iterations march downwards. And the non-stationarity takes the form of shifting this uniform distribution by a sinusoid to pi f t. So we have an amplitude A and a frequency f, which means that, let's say, over right here, we'll say is 1 over f. That's our period. We're adding a sinusoid that continues on through the duration of our training, where this height is our amplitude. You probably can't see that, so just imagine there's an A pushing this out. And if we sampled at, say, this time, so here we have t equals 0, at a different time, t equals pi, it doesn't matter, in the future, greater than 0. We're shifted a little bit to the left. And at some time later, we're shifted to the right instead. It's not quite the right picture, but I hope you get the idea. There's the center, there's the center. It's not the center. Okay, and what we're going to do with this problem, we're going to hold A as fixed. A fixed. And we're going to vary the frequency f. Vary f. And we're going to spend most of the rest of the talk wondering, and hopefully seeing, what happens to the loss. If we hold eta and mu where they converged for the IID setting, where do the frequencies lie that are problematic, or do they exist? Okay, so that's the non-stationarity. If there are any questions, again, I'm going to switch to make sure I can see the chat here. Hopefully these camera issues that I'm seeing in here are okay. Should it sum to t, or is it infinity? Is that already covered? I feel like it was, yeah, okay. Now I will go back to presenting the slides. Present now.
Yeah, Q for whoever who was pinned Kirby's video to unpin it now so that they can see the slides.
Okay, that hopefully now for everyone here, you see a slide that is titled SGD plus momentum, learning curve for stationary x sub t. And we see the loss curve that I speculated. It's kind of a dense purple cloud because there's 30 runs overlaid on top of each other. And each run, there are 30 of them, is trained with the same learning rate, the same momentum term, the same uniform sampling for now. And there's a random target and random initial model chosen. So the message here is we seem to have reasonable converging behavior. Is it optimal? Could we have chosen better parameters? Maybe, but the point is it seems healthy enough for now. The noise towards the bottom here is due to the observation noise, and it's due to sampling noise as well. So now we'll have a look at what happens when we sweep frequencies. Something. I'll just play the video here. So this is the same plot, and we're just sweeping frequencies. You can see the specific values changing in the title. We're sweeping over probably an arbitrary looking range that I chose, but hopefully that behavior that you just saw shows why I chose this range. At the very beginning, pause here. At the very beginning, we have frequency of 0, infinite period. It's exactly the non-stationary form. For small frequencies, in fact, I'll switch to the next slide because it is a bit more clear. For small frequencies, this is changing very, very slowly. The domain distribution is drifting very slowly, so it's not surprising that the same momentum and learning rate can sort of cope with it. They can drift sufficiently fast to keep up with the changing loss. And just as a reminder, this is our specific domain sampling distribution here, and this is what it kind of looks like for the first 200 iterations. We have it varying from negative 0.25 to 0.25 with an amplitude of 0.1, and over the course of 200 iterations, it completes maybe 3 periods or so. And that 0.16 frequency was chosen because it is right there. Oh, sorry, that's not what I meant to do. So I guess that the thing that I wrote that we were wondering about, do there exist frequencies for which we can drive this system to diverge, appears to be yes, or at least within the first 8,000 iterations, it does something that looks like divergence. Okay, so are there any questions about what's popping up inside of this video here, this frequency suite?
There's a question in the chat, Kirby.
Okay. What is non-stationary here? Only the domain, not the y's or the things. The non-stationarity here is only x sub I as you've written it. Only the domain is being sampled in a different way from time to time. The optimal weights, they don't change at all. So when I say the loss is changing, the stationary point of the loss isn't changing because the optimal weights don't change. It changes the shape of the loss surface in a way that I can maybe draw towards the end of the talk. Hopefully that addresses the question. What distribution was the test data sampled from? It's a big question. So it was sampled from uniform in the, I guess, the limb soup of the support. So we sort of, I'll just switch to whiteboard really quick here because it's much easier to draw. Okay. The stationary form was uniform from negative A to A, and we're treating the test distribution as negative A minus the amplitude and positive A plus the amplitude. And we just sample uniformly from there. That's not perfect because if we were to say, take the marginal distribution for like one period of the non-stationarity, we would end up with a distribution that resembles like a mirrored arc-coast thing. But for now, it's just the extent over which we sample over all time. Hopefully that answers the question. Another question. Should the non-stationarity be considered true x value plus noise, or the true x values themselves changing? So the true values, I guess to put it, I'm still whiteboarding here? Yes, I am. The true values are a stream xt, yt, and the predicted values are the y hats. So x determines our predictions and the true values. Hopefully that answers the question. I'm not missing something here.
Sorry, I hope I'm not derailing, but my question is, is the distribution shifting because of noise, like incorrect sensor readings, say, or is it shifting because it's actually shifting? The underlying data is actually shifting.
Well, this is a synthetic thing, so it is actually shifting. And if there's time, I can talk about a practical problem where this sort of shift can actually occur. I wouldn't characterize it as noise at all. This is a very smooth, drifting non-stationarity. I really hope I'm actually addressing that question. Okay, I'll present those slides again. Okay, so I'll just let this frequency suite video run a couple more times because it's kind of fun. We just see that for a couple of frequencies, there's a little bump and then some divergence. And we can look, rather than clunking around inside of a video, we can look at this inside of a single plot. So here on the left, we have the mean loss for the duration of our training iterations. We chose 8,000. And the x-axis is the frequency. So this isn't a proper frequency response. That's the quote, because it's not in terms of signal gain. But it's good enough to see the same phenomenon just in a single plot. So in the video, we're sweeping from left to right, and we eventually see a little bump in a loss and then a big spike in the loss. And again, just to be clear, this is a fixed learning rate, fixed momentum, fixed everything except the frequency. We're just changing the frequency. And perhaps you're wondering, how drastic are the changes in distribution, in non-stationarity across this little range? And the answer is not big. So this isn't even the whole video. This is just the domain sampling distribution where the first spike occurs, where the second spike occurs, and at the top and the bottom, we converged fine. So you can see, if you squint, there's a difference. It's not drastic, but it's there. And this is all, I mean, like I said, it's very specific. We're looking at a quote-unquote frequency response for a particular learning rate and a particular momentum. A domain distribution with a specific width translated by a specific sinusoid, and all the other experimental parameters that are fixed here. And near the end of the talk, we'll back out and try and paw at some more general statements. But for now, based on what we've seen, it's natural to ask, if I have a particular learning rate and momentum, where are these bad frequencies that drive my learning system to high losses or possibly divergence? And it's natural to address that with a sort of a heat map thing. So this is a very similar plot where each row of this image is just a heat map version of the plot we were looking at before. So each row is a momentum. This whole thing corresponds to a single learning rate, and we're looking for frequencies that cause problems. And the message is that these sort of white-hot regions for learning rate 0.004, they are the bad combinations of momentum and frequency for this particular non-stationarity. And it's difficult to look at a 3D image, but we can look at a few slices. So again, this is, each image here corresponds to one learning rate. Each row of the image, a momentum value, and the columns here along this x-axis are the frequencies. And you could conjecture about what trends might hold outside of this very tight little set of ranges that I chose. Small momentum values, safe. Sufficiently large momentum values can be risky in general, kind of across the whole range of frequencies, and there's a particular frequency that can hurt them. So that was just kind of a blast through some empirical results. I'm going to address some questions and make some concluding remarks in front of my whiteboard here. Very quick concluding remarks, I suppose. Stop presenting here. So I should be the full screen now. You might be asking, why linear regression, of all things? Well, it's simple and it's a nice starting point. It's really well understood. And extension to higher dimensions and nonlinear function approximators are natural next directions, but they are problems for later. And you might also be asking, why a sinusoidal non-stationarity? Why worry about such specific frequencies? Well, it's common to approximate a dynamical system's response to general periodic input with simple sinusoids. So, for example, if we were in a problem that a question alluded to earlier, where the non-stationarity was periodic, not very sinusoidal, but due to some very real shift that's happening in, for instance, sensors changing, or maybe in a web application with very periodic nature from daily, weekly, and yearly traffic, you can have covariate shift like this. Anyways, it's very common to approximate periodic inputs with sinusoidal, with simple sinusoids. And I do feel that for some learning systems, one could get, hopefully, a closed form determining which frequencies diverge in terms of the hyperparameters, or at least approximate bounds on where those dangerous frequencies are. And the reason that might be important, if you know your continual learning system will be exposed to periodic covariate shift like this, of a certain frequency, weekly, annual, who knows, you could use that frequency to calculate or at least estimate what combinations of learning parameters might be resonant with your learning system and might be dangerous. In offline learning, we can just try combinations, run them, and pick the ones that don't diverge, and that's fine. But in a continual or online setting, that's not really an option. And if we have prior information, like periodicity, about our non-stationarity, it would be nice to use that information to avoid hyperparameter configurations that are unstable before we actually deploy this system. I should stop there. There's more to say, but I should definitely stop there. We are time up. That's true, right? Yes, that's true. I see silent claps, and I do appreciate it. So I see that there are some questions here. How did you encounter this phenomenon? Well, I made it up. Actually, this phenomenon was Siobhan's audio crazy for anyone else? Okay. Phew. That was a square wave. So Siobhan has two questions. How did you encounter this phenomenon? Can this shift also happen while mini-batch learning, say for an unfortunate sampling strategy? Yeah, okay. As long as I understand the questions. Yes, and they're all related. So, for example, the business of software as a service web applications, like Netflix or Google Play Music or any number of people that love to employ us software people, they're very used to seeing high periodicity in their traffic, not just in traffic volume, like day to night or week to week, weekend versus weekday, seasonality from summer to winter. Lots of these types of businesses can have lots of volume change that's highly periodic, but also if you are, say, sampling the genres of movies being watched, you can imagine weekly periodicity in the genres being watched, or maybe even aperiodicity. But the point is, periodic covariate shift is a phenomenon of very real data streams that we love to train or would love to train continual learning systems on. So that's how I think this sort of phenomenon could be encountered in real life. Is Netflix running a linear regression model for their recommender system? No. But, like I said, extensions might be worthwhile. Another question here. Oh, sorry, I didn't address. Can it also happen while mini-batch learning, say, an unfortunate sampling strategy? Well, if we have that underlying sinusoid that I drew, one could imagine an unfortunate sampling strategy being, well, that would be good. The point is, if we have a highly aliased sample such that we train on a mini-batch drawn here and then train on a mini-batch drawn here, we have sort of a pathological bad time that can really mess with the condition of the loss surface. Okay, maybe I missed it. This is from Hassan. Maybe I missed this part. Can we express other forms of covariate shift as sum of periodic components, like Fourier transform, and get similar results? I could only make speculative claims about getting similar results, but you can certainly take nice, easy stabs at covariate shift by looking at some stationary distribution, like a uniform or a Gaussian, and applying some sort of signal, maybe a composition of Fourier basis, to get a smooth drift, or even non-smooth drift. You might have a point here is if your distribution is piecewise stationary, like we like to use in catastrophic forgetting benchmarks, then you can also try and model that in a synthetic way by using a fixed source of stochasticity and adding a signal that we can actually comprehend to it. I think this is why experience replay is used in DQN. Yeah, I'm much more a supervised learning person than a reinforcement learning person. So, but as far as I understand, for non-stationary, like non-stationarity is a big problem there. And experience replay, I think it's an instance of the memory-based ways of addressing forgetting. Make sure that you store enough data from the past that you kind of soak up the variation. That's as far as I understand it, but you're definitely right. Is it correct to assume that this only happens when momentum is present and there is an exact equivalence with resonance that the system has some effective mass stiffness? This is a really good question. So with momentum, it's certainly more likely, because if I were to use a more correct frequency response plot, so with a proper frequency response where we have our range of frequencies f and signal gain, our system has a resonant frequency, specifically when gain is higher than unity. So this is 1.0. And a momentum term introduces a second-order dynamic, like second-order dynamics in time, not in weights. Basically a second derivative to the time dynamics. So you end up with some region of frequency with higher than unity gain, and that's what induces the ability to resonate. And that's all with asterisks on it, because this sort of frequency response gain plot, I'm pretty sure this only applies to linear dynamical systems. If you have a linear dynamical system, then your system response will only be at the same frequency as the input that's driving it. With nonlinear dynamics, it gets wild. The amplitude and the frequency matter, and you can end up with things that don't even look like functions. And the dynamics in time, I think even for linear regression, I don't think that's a linear differential equation. So you do end up with nonlinear stuff driving the frequency response.
I wanted to ask a related question. I said that the updates are simple gradient descent with momentum, and that's a second-order linear system that transforms the sequence of inputs into weights. Like you can describe that as a second-order linear system, which seems to be a very good fit for this previous question and the critical frequency for that second-order dynamical system. But like it seems that you're thinking that you don't have a linear system. But I think that you do have a linear system if you view it as transforming the sequence of inputs to a sequence of weights. that's a linear transformation. Every step is kind of like a linear update.
Okay. The reason that I claimed possibility for nonlinearity is coming from a little bit of research that I did into the physical systems that people use to talk about these things. There's like the heavy ball momentum, where you have in linear regression a quadratic loss surface, and like a heavy ball momentum, it's a particle with momentum, and the time dynamics of a ball in a parabolic bowl are they're not a linear, it's not a linear differential equation. From one step to the next in the discretized form, maybe that's where the linearity lies? I don't know. This is trying to appeal to physical analogy, so maybe it is misguided from the beginning.
So for these algorithms, there is this ODE-based analysis where you let step sizes go to 0, and then the resulting algorithms, okay, as a function of how they work on updating the parameter vector, they're described by linear systems. So
Okay.
linear updates. Yeah, in that
I
limit.
wanted to chime in there. So maybe there's like so what Shaba was saying, it's a second order system, which means that it's not just linear in the weights, but also the delta of the weights.
Yeah, it has a memory.
Yeah. So Kirby, so maybe, yeah. So, and that's what momentum-based algorithms are doing. They're not just making the next update based on the last weights, but also the change in the last weights.
Yeah. Yeah, that's even in a linear system, that's sort of that's what can give rise to greater than unity gain. I'll have to, I retract any claim of potential for nonlinearity. I'm going to reread those continuous domain papers and have a closer look at the dynamics.
Yeah. I just have one suggestion along these lines, because SGD is, like the learning rate in SGD is mixing together two things, which is sort of the size of the gradients and the size of the noise. And the optimal learning rate kind of depends on both of these in sort of a confusing way. And so maybe it would be interesting to repeat this experiment, but replace all of the noisy gradients with like the expectations of those gradients. So the gradient becomes what the expected gradient would be under the current distribution. And then you might see all the frequency responses more clearly.
Would you expect that to be approximated by using enormous batches at each time? Would that be a way of, say, getting a nearly perfect estimate of the expected gradient rather than the gradient?
In the stationary sense, yes, but the problem with the non-stationary sense is that your batch is also averaging over time. And so it is kind of smoothing over time as well. But what I want is just smoothing over the randomness at a particular time step.
Okay, okay.
And that's what I would want to understand that separately.
I agree. That would be very interesting. I think the theoretical direction that I would like to take this is it's along the lines of the kinds of work that Chaba was suggesting, where you write discrete update rules as a finite difference, take learning rate to 0, and it turns out that, well, it turns out that the gradient descent update rules are Euler discretizations of a continuous system. And working with these frequency responses in the continuous domain is a lot more friendly. And I think that would, where was I going with that? I don't recall.
Maybe along those lines, I was going to see whether you had started to do any work on those lines to see what kind of, I'm assuming that you have a mechanical intuition for how this is behaving, like when you're looking at the signal response and everything. So have you at all looked at this sort of seeing it as an Euler discretization of a dynamical system? And then does this suggest, like, is it spring-like? Like, you know, what's the return force that drives your model to where the current parameter is? Like, is it more like a spring, or is it more like your heavy ball in a parabolic dish, which is just like a mess?
As I I've only come across a couple of papers that make an explicit effort to use a physical analogy because the differential equations are so close. And it looks like, depending on how you write, like, what's an example of this? If you look at SGD with momentum classic and SGD with momentum, like Nesterov momentum, apparently the difference is in the continuous domain. They can be written in the same continuous form, but they are different discretizations of the same system. So the SGD update was just a vanilla, like, forward Euler, but the Nesterov was the implicit kind. I think I'm remembering that correctly. And there's some papers, I can share them afterwards, that try and explain, like, what kinds of spring mass damper is this? The neatest one was SGD. Actually, no, never mind. I hope that will take more time than we have.
Yeah, I guess maybe just a follow-up question is, because I guess like the first thing that comes to mind is just like this damped spring sort of example. And if you try to make SGD with momentum sort of analogous to this, then when you look at your resonance curve, you'd expect like a single resonant frequency that somehow relates to, like, you know, how massive the system is and how strongly it wants to return to this. But that's not quite what you see, right? It looks a little bit more complicated than this. You have this sort of like double peak. Do you have any sort of intuition or ideas about why you're seeing like this more complicated, I guess, resonance structure?
Yeah. Yeah, I do. So where's my eraser? There it is. If you have a parabolic bowl, the level sets look like this, and it's sitting over top of a set of axes and going vertical Z. If you have a point mass constrained to this surface, and it's just following like gravitational energy minimization, and there's no friction, your dynamical system is written in terms of like x dot and x double dot, and these are all vectors. In this physics example, where you just have a point mass following its energy minimization path, the differential equation that describes the trajectories are nonlinear. You've got like derivatives multiplied by non-derivatives and things raised to the squared in the differential equation. And in that situation, you no longer have a linear system, so you don't have such a straightforward input frequency to output frequency singular relationship. You can have all sorts of crazy stuff erupt. You can have the input frequency amplitude and input signal amplitude and frequency determine where the harmonics lie, and that gives rise to those classic like complicated frequency response things. However, does this exactly apply? Is SGD with momentum a forward Euler discretization of this exact system? I have work to do to figure that out. I don't know.
Sorry, Kirby. So did you say that this is like the system had no friction? It was a parabolic, like quadratic system.
Yeah.
I think the updates in that are actually linear. If you don't have friction, you get these second order differential equations where the update depends not on the velocity, but basically you get that the acceleration is a quadratic function of the position.
I will link to Physics Stack Exchange post where they showed this the dynamics to this specific ball thing, because maybe I'm just misinterpreting that or something.
And I think if you add any sort of complication, if you add any friction and stuff, then it is true. That's what you say.
by the way, so regarding this physical viewpoint, so when you're changing the input distribution, I mean, like, you're kind of changing a little bit things. So what's really interesting is that the optimal solution is the same, but of course the covariance matrix for the linear regression problem is going to shift around. So it's like this surface is kind of like maybe like pulsing or something like that. And as you're making it pulsing, as it's in the bottom of it, if you want to use the physical analogy, you can make the pulsing rate the same as like whatever like internal like dynamics the system has, and that is what makes it like go wide and crazy, I think.
Yeah, I think you're right. I did a little bit of messing around with plots, and if you look at the loss surface, say we have like theta star at 1, 1. If we look at the loss surface induced by sampling at 1, x equals 1, we get level sets in the loss that are ellipses aligned with this. So this is for x equals 1, and these are the level sets of the loss. And if we look at the same plot for x equals -1, theta star has not moved. The level sets instead are aligned with -x. So as we shift this sinusoidally along, we're taking the loss surface and without moving a stationary point, wiggling it kind of back and forth.
Right.
It's similar to the way we talk about the conditioning. I think it's the conditioning of like XTX,
yeah,
the projection matrix that brings us a closed form.
So you can imagine that if you had a heavy ball on this with some friction or whatnot, I think that if you don't have friction, the ball never stops. So you definitely want to have friction. That it would still wiggle around because you have input to the system, like you're driving the system with some energy input, and then that could also be like just generating a lot of response from the system. And so maybe altogether it doesn't blow up to infinity, but it's like you can keep a lot of the energy, maybe.
Yeah, I agree.
So on that note, I also wanted to visit sort of the online learning version of this problem rather than the gradient descent mechanical version of this problem. Yeah, so it disappeared. So I'm thinking about sort of what role momentum plays and what role the learning rate plays, right? So basically, to a first approximation, the momentum is supposed to tell the algorithm how much you expect the loss surface to change from one step to the next. Like that's what it controls for. And the learning rate to a first approximation controls like how big the gradients are. Right? So for example, forget about noise for now, right? So when I talked about like getting rid of SGD and just having gradient descent with changing loss surfaces, right? So that's what the momentum and the loss are doing. And usually when the loss surface is the same, the momentum is just controlling for the smoothness of the loss, right? Because if you take a gradient at one step and then you move a little bit and you take the gradient at the next step, because if the loss function is smooth, then those won't change a lot. And that's what the momentum is taking advantage of, right? And then the learning rate is like basically controlling for how big the gradients are. So if you rescaled all the loss functions, by some constant, then you would have to scale the learning rate also by that constant, right? That's a basic intuition. And now I'm thinking about like what we know about like dynamic, like these algorithms that are not chasing any particular loss function, but they're chasing a sequence of loss functions over time, right? And gradient descent like works pretty well, as you have found. But one of the things I will say is that in many situations, it's not the right thing to have a single learning rate. So if you consider an algorithm with a single learning rate, sure, there is a particular learning rate that's the best setting that's matched to the inherent frequency of the system and so on. But often you can do better by adapting the learning rate as time goes on. So you can kind of think of it as, like you're adapting to sort of the stationarity of the problem, and that's changing, but on a short enough time scale, you can do better by doing that, right? So one of the papers I've been reading right now is like about this dynamic regret idea. And sort of the very simple idea for that is that you get a regret bound that depends on how much the loss functions are changing. So if you look at the change in the loss function from one time step to the next, to the next, to the next, that's kind of giving you a path length, right? So for example, for the sinusoidally changing loss function, the path length would be the distance moved along the sinusoid. Then of course, if the loss function is totally constant, then that is the shortest possible path length, right? And so you can get algorithms whose regret against changing loss functions depends on the path length that the changing loss functions are covering, which is really nice. And the basic idea on how you achieve that is basically that you run multiple instances of the algorithm, and one version of the algorithm is just like run for the entire times, like for all time. And then you run another instance of the algorithm that works on like windows of half the horizon and so on, right? So you split up your time interval into a set of logarithmic time, like set of time intervals. And then you run one separate algorithm on each of them. So you have one algorithm running on a long horizon, one running on half the horizon, another running on half of that, and so on, right? And the nice thing is, okay, so now you're saying, okay, what are these algorithms doing, right? Like, what are they chasing? How are they dividing the work up amongst themselves? And the idea is that each algorithm is learning the residual from the last one. So sort of the first algorithm is trying to figure out like the correct set of weights over the long run. And then the next level down is trying to figure out how much the weight should change from the output of that base algorithm, and so on at different time horizons. Does that make sense?
Yeah.
Yeah, and so what you need these algorithms, the key property that you need these algorithms to satisfy, so that you can just basically add up their results, and they give you a good prediction for like the actual weights, is that the algorithms have to be strongly adaptive. And what that means is that they are all adjusting their learning rates, etc., based on the inputs that they're getting. And so this sort of general scheme of combining together online algorithms seems to have really good regret properties for when you're chasing, when you're chasing sort of changing targets. Yeah, and then the momentum is another complication on top of that. But of course, the momentum is also, like in this case, the momentum is going to be tied to how quickly things are changing, right? Like how quickly your loss function is changing. And so the work that I'm talking about, which I'll link to later in the chat, also talks about like how do you adapt momentum when you have strongly convex loss functions, which we do in this case. They're quadratic. But yeah, so lately, I just wanted to say that lately there has been like a fair bit of good work on online learning in these sorts of settings. Oh, and there has also been related work on how the online learning results transfer over to stochastic and back and forth. So it might seem weird that the gradient descent thing, which is based on the stochastic idea, it turns out that it's very roughly the same problem as the online learning thing. So another approach to try.
I would very happily read that paper. That would be awesome. Well, I suppose if there are no further questions, Abhishek, should we wrap it up? Or are there other questions that I missed in the chat? I completely forgot about the chat.
I think that's about it.
Yeah.
Let's thank Kirby for the cool talk.
Thank you, folks.
Thank you.
Kirby, so did you solve this?
Did I solve it?
Yeah. Is there a method to avoid this?
Yeah, I mean, Roshan hinted at the notion of using good adaptive learning algorithms, or like the like regret minimization perspective. Like, basically, use a smarter optimizer and don't use fixed learning rates, and you will end up, in this instance, converging to the right place.